So we've got a question here on using the normal approximation for the binomial. Okay, if the binomial distribution meets two conditions, that n times p is greater than 5 and n times by 1 minus p is greater than 5, then you can use the normal approximation to the binomial. The mean of the binomial is n times p, which is why we've got that here. The variance of the binomial is np 1 minus p, which is why we've got that there. One thing to point out, which I mentioned earlier for those in the class, the binomial is a discrete distribution, the normal is a continuous distribution, and we'll have to bear that in mind as we go through this question. So we've got a question here. Example number 1, a fair die is thrown 40 times. Part A, use the binomial distribution to find the probability that 3 6s are thrown. So I'm going to ask you guys just to do that now. That's S1 work. Then in part B, we're going to do it, repeat the same thing, find the probability that exactly 3 6s are thrown using the normal approximation. And in part C, we're going to use a suitable method to find the probability that more than 10 6s are thrown. Now I'll just point out, if we were doing this with the binomial distribution, we'd have to do the binomial sum about 10 or 11 times, add them all up, and that would take ages. So I'm hoping that Luke will give me an answer to part A nice and quickly. Luke did get an answer. Okay, he got it correct. So what we had was x for the binomial distribution, n is 40, p is 1/6. We had the formula down here. So it was n choose r, p to the r, 1 minus p to the n minus r. Or if you've got a graphics calculator, you can just enter the n, the p and the r and get the answer out. And it was 0.0538. So that was part A. That was just revision from S1. Now in part B, it's asking us to do the same thing using the normal approximation. Now I know here it tells us to use the normal approximation, but let's just check it's valid. So we need to check np and we need to check n 1 minus p. Well, n is 40 and p is 1/6. 40 times by a 6, or 40 divided by 6. Well, that's going to be 6 point something. So that certainly is greater than 5. Then over here, 40 times by 1 minus p, which is 5/6. Well, that's in the 30s. That's definitely greater than 5 as well. So because those two conditions are met, that means that our x, which was binomial, 40 1/6, can be approximated by the normal distribution, n times by p. So now I need to know exactly what n times by p is. 40 times by a 6. What's 40 times by a 6? Well, 6 of 40. 6.6 recurring. Okay, well, we'll stick it at 6 as 2/3. Keep it exact for the time being. And then over here, for the variance, I need np 1 minus p. Well, that's the np, so I now need to times that by 5/6, which is 1 minus p, to get the variance. And what will I get? Can we do it in fractions, if possible? We've got 30 and a third, okay, as the variance. Okay. So we want now the probability that x equals 3. Okay. Just going back to something we did earlier in the lesson, what's the answer for the normal distribution, the probability that x equals 3? Without any calculation, what's the answer? Probability x equals 3. 0. It's a continuous distribution. That's going to give us a 0 answer. Okay, because the probability of getting any specific value on the continuous scale is going to be 0. We can't do that. We've got to change it. Now, the notation I use, and I suggest you use it as well, is I'm going to put a little b here by that x, because that was based on the binomial distribution. And we're going to change that now to something on the normal distribution. So I'm going to put an approximately equal to here. What is that going to be? How can we change that? How can we go from this discrete to this continuous, do you think? Any ideas? Yeah, okay. A window between in which the value lies. 3 lies between 2.5 and 3.5. Okay. So, if I now want, so that shouldn't have been a closed bracket there. That's an x equal, no it isn't, sorry. Should have been a bracket there after all. So on the probability between 2.5 and 3.5, for my x, and I'm going to put a little n there now just to show that this x is now under the normal distribution. So, are we all happy from there? Instead of doing 3, we're doing between 2.5 and 3.5. Eve, happy with that?
Very happy.
Okay, so we've done these before in ranges, and it's going to be phi of the big number, take away the mean, over the standard deviation. So what is wrong with what I've written down there so far? I'm going to do the other one over here, the small number. But something's wrong. Not the signs. Something's wrong about what I've written down. So inside here I'm having x minus mu over sigma.
Oh, very.
Yeah. This I've written down is the variance. Remember, it's a standard deviation you need down there. So I need those square rooted. Okay? So, if you've got graphics calculators, you can do this quicker than if you're using the tables. But you do need to convert these to the z values. So if you can do those and tell me the phi values you're going to use, okay, for the first one and for the second one. Right, we found an error here, okay, because when I asked the class to work these out, they weren't agreeing with me. Up here, this variance was wrong, okay, we should have spotted it as we did it. That should be np times by 1 minus p. And I asked somebody to do 6 2/3 times by 5 6. Should have realised that it couldn't have been that. That number there should have been 5 and 5/9, which means we have to change inside the square root here. 5 and 5/9 and 5 and 5/9. Okay. So once the class had changed that, we'll come back to what these brackets, what the values in the bracket should be. Okay, we've got our first z value. There's no point in working these out if you're using tables to more than 3 decimal places, because that's as far as the z values in the tables go. We got it being minus 1.344. Okay?
And minus 1.768.
And minus 1.768. That agrees with what I've got. Just one thing I'll point out here at this stage, okay? So if you've got 4 guys, can just watch this as well. What we did here when Brent said we need a window around 3, when you go here with these halves, and it's always halves you use, this is called the continuity correction. And you need to be familiar with that phrase. It's because you're going from discrete to continuous, and because you basically go half a unit either side the number here. It's called the continuity correction, and you need to be aware of that phrase. And every time you're using the normal to approximate the binomial, you will need to get in there that continuity correction. So you've got these two values. We can now go straight to the calculator and work out the p values of these. So you could do, using the graphic calculator, p of that, take away p of that. But what I'm going to do is do the working out without a graphics calculator. And if there's a negative phi value, you've got to do 1 minus the positive phi value. So that's that bit over here. The negative value inside the phi, that's 1 minus phi of the positive value. But all of that bit had to be taken away from the bit at the front. So if you're doing the tables, you're going to get this. And as you're doing this here, I've got a 1 here, and in here I've got a minus 1. They will cancel each other out. I hope you're watching, Luke. Okay? Yeah. The 1 here, if you're doing it on the tables, that 1 and this minus 1 will cancel out. So you're going to get here minus phi of 1.344. That 1 has disappeared, and the minus there will mean a plus eventually goes in there. So if you're doing it with the tables, you'll get that. If you're doing it with the graphics calculator, you should get a similar sort of thing. For this one over here, has anybody done this phi-ing bit here on the calculator and got a value for me? I know what it should be from tables. Any of you got a number? I know, so have you done it from the tables at all? Do it from the tables and see where you get. Okay, I'll stop the recording for a minute. Okay, so by doing this, if you've used the graphics calculator, you can go straight from this line or even this line here down to the answer. If you've done it in the tables, these are the values you should get from the tables. That's what I got from the tables, 0 from 0.510. Emily, if you've done it all on a calculator, what was your final answer?
0.050944.
Okay, so basically they're the same. The for three decimal places, they're both 0.051. So from the normal approximation, 0.051. From the binomial, 0.054. So they're out by 0.003, which isn't really very much. Brent's worked out to be about 5%. So that's a question where you use the normal approximation and the continuity correction for a binomial distribution.